Okay, hey everyone, welcome back to our series on linear algebra lectures. Today we'll be finishing up chapter 5, so section 5.3, and we'll be talking about the Gram-Schmidt process and QR factorization. We'll talk about what both of those things are in a moment, but first we have to address an elephant in the room for chapter 5. We've kind of been singing the praises of like orthogonal bases and like, oh man, these orthogonal matrices have these wonderful properties and this, that. Well, the problem is we don't know for sure that every subspace has an orthogonal matrix or orthogonal basis. And even if we did, the only strategy that we have for finding the orthogonal, like an orthogonal basis or whatever, is to like solve some gnarly system of equations and hope for the best and kind of like almost patch it together. So this is going to resolve that issue kind of we're going to put a pin in the coffin very finally. Yeah. So here's round one of the strategy. So given some basis for a subspace, given a basis for a subspace, go and construct an orthogonal or even an orthonormal basis, one vector at a time. And we'll do round one here with this example. So W is the span of these two vectors, 1, 1, 0, and negative 2, 0, 1. The solution that we're going to use is just literally take x1 and the component of x2, which is perpendicular to x1. Okay, so x1, done. That's just 1, 1, 0. That was easy. Okay, what is the component of x2, which is perpendicular to x1? So that's let me write it. The perpendicular component to x1 of x2 is precisely x2 minus, this is going to be totally helpful, the projection of onto x1 of x2. In other words, you have x1, you have x2. Let me do something a little bit more dramatic. There we go. What we do is we project x2 onto x1 so that you have a right angle here. Okay, this piece of x1, or the vector that's parallel to x1 anchored at the same place as everything else, but which has the same component in the x1 direction as x2, that thing is proj x1 of x2. And by vector subtraction, whatever the other thing is, that's perp x1 of x2. Okay, and this is what we talked about in the last video. But the idea is that that thing is now orthogonal to x1, but is still inside the subspace W, right? And so we want to go and construct it. So to do that, all we need is what is prod x1 of x2, and that is, we have a formula for it. It is x1 dot x2 divided by x2 dot x2 all times x2. Sorry, all times x. I got this exactly backwards. We're projecting, we need to subtract off an x1 component, right? So it's x2 dot x1 divided by x1 dot x1 all times x1. We need to subtract off something that's happening in the x1 component. We have to subtract off exactly the right amount so that the only thing that remains happens in some new orthogonal direction. That's this. Okay, and this is just a computation. This is x2 is negative 2, 0, 1. x2 dot x1 is -2. x1 dot x1 is 2. And x1 is 110. So this is -2 plus 1, right? Minus -2 over 2 is just 1 times that vector. Actually, we could just write it. It's just going to be x1 plus x2. So -1, 1, 1. And so our basis for W is 1, 1, 0, or x1, and -2, well, -1, 1, 1. Note that this new vector, this is just x2 plus x1. So it's definitely inside of W, right? It's a linear combination of the original basis vectors of W. But that's also true because, look, we just took a linear combination of those vectors. So we're never going to leave the subspace by doing this. Okay, that was one iteration of the Gram-Schmidt process. However, W was a two-dimensional subspace. What if we had more dimensions? So let's do it. I will tell you what the Gram-Schmidt process is. You might not like me for this, but that's okay. We'll get through it. So the Gram-Schmidt process is given as Theorem 515 in the book. It not only says that, first of all, every subspace has an orthogonal basis, it also gives a procedure for constructing that basis, given any basis. So, yeah, it's pretty great. So let W be a subspace of Rn, and suppose that we have a basis x1 up through xk. And we define the following. So v1 is just going to be equal to x1. Starting off strong. And then after that, if you want more vectors v, then like v2 or v3 or whatever, vj in general is going to be the projection of xj onto the subspace wj minus 1. Should be less than or equal to k. That'll be for any future value of j. So for any future v vector that we're trying to define, yeah, we have to find the component of xj, which is perpendicular to the subspace wj minus 1. What is wj minus 1? Well, any wj minus 1 is just the span of the vectors that you've computed previously. So in other words, what we're doing is we're using the original basis vectors as a model. We know that they're all linearly independent, and so what we do is one at a time, we sprout off a new subspace, wj. W1 is just the span of v1, which is just the span of x1. W2 will be the span of v1 and v2, okay, w3 and so on, right? But what we're doing is every time, in order to get a new, the next iteration of the subspace, we sprout off the component of xj, which is perpendicular to the previous subspace. And we know that there will be a non-zero component like that. Otherwise, the vectors would be linear. The basis vectors here would be linearly dependent, which is impossible, right? Okay, great. Okay, so that's the definition. That's how we start. What do we know? What we know then is that for any value of j, the wj's that we've defined here, spanning these new vectors, whatever, is the same as spanning the first j vectors of the original basis. They span the same vector subspace, and the new basis, the new set of vectors that we're using to span that subspace, is an orthogonal basis for wj. The reason we care about that is that once you get to the very end, the last one, you've now got k vectors, v1 up through vk, which form an orthogonal basis for the original subspace w, which is the same as wk. Pretty gnarly. And it's the kind of thing that you really only need to see it once And then you just have to grit your teeth and do it several times. So this is going to be fun. And we're going to do the hardest problem we can possibly imagine. Okay, it's not that bad. It's just three vectors in R4. So it's a three-dimensional subspace of R4 that we're looking at. And it's asking us for an orthonormal basis. Just do it. Okay. Orthonormal, meaning it's not enough to give an orthogonal basis. They want us to normalize our basis vectors when we're done. All right, v1 equals x1 equals 1, -1, -1, 1. Starting off strong. v2. V2 is not as bad. This is like the same caliber as what we did before. It'll be x2 minus x2 dot v1 over v1 dot v1 all times v1. After all, right? This is the perpendicular component of x2 to the subspace spanned by v1. Okay, and that's just 2, 1, 0, 1 minus, okay, dot product x2 with v1. That's 2 minus 1 is 1, minus 0 plus 1 is 2. Over. v1 dot itself looks like 4. So it'll be minus 2/4 or 1/2 of 2, 1, of v1. So 1, -1, -1, 1. As a vector, that's okay. So we're gonna just scale the v1 vector by -1/2, which means all the positives become negatives and all the ones become 1/2s, and then we'll just add them, add the two vectors together. So 2 minus 1/2 is 3/2. 1 plus 1/2 is 3/2. 0 plus 1/2 is 1/2. And 1 minus 1/2 is 1/2. I hope we did that right. I'll be following the book's example for this one because the last thing you need is to watch me make a computational error. This is correct, apparently, for v2. So we have v1, we have v2, v3. Okay, so far you're thinking, what's the big deal? This is way easier than we thought, and why didn't we leave with this? All right, v3. Okay, v3 is x3 minus the projection of x3 onto v1, x3 dot v1 over v1 dot v1 times v1 minus, well, okay, I'm gonna, it's not right for me to write this just yet. Let me actually write this out because unless you are very comfortable tracing through the definition of the component of x3, which is perpendicular to the subspace w2, let me write out all the definitions. So this v3 is none other than perp w2 of x3. Okay, no tricks in this one. No tricks. Which is also just x3 minus proj onto v2, v1 well, both v1 and v2. Proj v1 of x3 plus proj v2 of x3. You should recognize that as the definition of the component of a vector perpendicular to a subspace. v1 and v2 are basis vectors for that subspace by construction. W2 is literally the span of those vectors. And so the component of x3 perpendicular to that subspace is x3 minus the sum of the projections onto each of the basis vectors. There we go. Sum of the projections on each of the basis vectors. Add those together, subtract that away from x. But now we have to write the formula, and this is what I was about to write down. So didn't really cost us anything, but now you see where what I'm writing is coming from. All I did was trace through the definition of what is perp W2 of x3. But yeah, okay. This is x3 minus, here we go, x3 dot v1 over v1 dot v1 all times v1. I'm distributing the minus sign, so putting another minus. x3 dot v2 over v2 dot v2 all times v2. Okay, so to do this, we're going to need to take some dot products. Now, we already know precisely one of these. We know v1 dot v1. It's 4. What's that for? We did it once already. The other 3 we have to compute. Okay, so this is, I'll probably write as many vectors at once as I can. So 2, 2, 1, 2 is x3. Minus, all right, x3 dot v1. That's 2 minus 1 plus 2, which is 1. And then v1 dot v1 is 4. We already computed that. This is all times v1. 1, negative 1, negative 1, 1. Okay, x3 dot v2. x3 is 2, 2, 1, 2. v2 is 3 halves, 3 halves, 1 half, 1 half. Okay, the dot product is going to be 3 plus 3 plus 1 plus 1 half. So 7 and a half, 15 halves, divided by v1, v2 dot v2. So v2 dot itself. That's 9 fourths, 9 fourths, 1 fourth, and 1 fourth. So 20 fourths, so 5. Well, that's kind of nice. Times v2. 3 halves, 3 halves, 1 half, 1 half. And now, let's just do our vector arithmetic. I'm going to write this as a single vector with a bunch of line item arithmetic problems. It's the easiest way I can think of to do this. And we can also clear out some of the fractions. So this will be like 2 minus 1 fourth, and then minus 15 halves divided by 5 times 3 halves. Okay. That's just 3 halves times 3 halves. So minus 9 fourths. And then the next one will be 2 plus 1 fourth minus 9 fourths. Then the next one will be 1 plus 1 fourth minus 3 fourths. Just making sure. And then the last one will be 2 minus 1/4 minus 3/4. And we can just do the arithmetic now. So 2 minus 10/4 is like 2 minus 5/2. So negative 1/2. 2 minus 8/4 is just 2 minus 2, which is 0. 2 plus 1/4, yeah. 1 plus 1/4 minus 3/4 is 1 minus 1/2, which is 1/2. And 2 minus 4/4 is 2 minus 1, which is 1. How'd we do? Great. So our basis, our first pass, orthogonal basis. We've got, well, of course, we've got 1, 1, negative 1, negative 1, 1. And then we've got the one with the halves. 3 halves, 3 halves, 1/2, 1/2. And then the last one is negative 1/2, 0, 1/2, 1. Now, having all the fractions in sight is awful. And what have we just constructed? We've just constructed 3 vectors that are all like pairwise at right angles to one another, right? Whatever that's supposed to mean. And so we're left with, okay, they're not great vectors. But notice, if I scale any one of these vectors, I'm not changing the property that they're pairwise orthogonal, right? So instead of writing 3 halves, 3 halves, 1/2, 1/2, I can just scale it up by a factor of 2. 3, 3, 1, 1. If I had done that, you can check. If I had done that even at this step, to create V2 is 3, 3, 1, 1. If I had done that up here, you can check that it would still work. It would still work exactly as planned. You would end up with an orthogonal basis at the end. Same thing here. We can do negative 1, 0, 1, 2. Remember, to scale a vector, you have to scale all of the components at the same time. This will at least clear out fractions and some square roots, actually. However, the problem did not ask us for an orthogonal basis. It asked us for an orthonormal basis, which means we have to scale our vectors, again, even though we scaled them once already, so that each one has length 1. So now we compute, so this is V1, this is V2, and this is V3. Technically, this is like V1 prime, V2 prime, V3 prime, because we didn't get exactly the output of the projection onto each component. We did the perpendicular components, whatever, and then we scaled them up so that we had integers in the components. So technically, it's not V1, V2, V3. I'm abusing notation, but like they're basically the same. And regardless, we're about to change them again. So let's define Q1. Q is the letter that we like to use for normal vectors. So Q1 is going to be V1 divided by the norm of V1. Actually, let's just be lazy and say that's true for Qj. Q1, Q2, Q3, they're all V1, V2, V3 divided by their norms. So let. Okay, then Q1 is 1 over, what is the norm of V1? It's the square root of the thing dot product with itself. So that's square root of 4. which is 2. Which is, so we're doing 1/2. We're back, okay, we're doing 1/2 times 1, negative 1, negative 1, 1. So this is 1/2, negative 1/2, negative 1/2, 1/2. And now we can't scale it back up. Do not scale it back up, because as soon as you do, the norm of your vector will fail to be 1. The norm of this vector right now is 1, right? But if you scale it up, then like literally you're stretching out the length of the vector. It will no longer have length 1, of course. So don't do that. Instead, just leave it as it is. Sadly, we can't rescale this time. If it was asking for an orthogonal basis, we could, but it's asking us for an orthonormal basis, which means we need normal vectors, unit vectors, that is. Okay, Q2, let's go. We're almost done. This is going to be 1 over the norm of V2, which is 9, the square root of 9 plus 9 plus 1 plus 1, square root of 20, which is 2 root 5. Right? 4 times 5 is 20. Times 3, 3, 1, 1. Which is, okay, 3 over 2 root 5, 3 over 2 root 5, 1 over 2 root 5, and 1 over 2 root 5. Oh, wonderful vector. Q3. So that'll be 1 over the norm of V3, which is 1 square root of 1 plus 1 plus 4. So root 6, 1 over root 6, times negative 1, 0, 1, 2. Which is negative 1 over root 6, 0, 1 over root 6, 2 over root 6. And it just is what it is. These are our vectors. Oh, I just looked down. The book rationalizes the denominators. I mean, we probably should too, but I'm not going to. Thus, orthonormal basis. Let's just write it one more time. 1/2, negative 1/2, negative 1/2, 1/2. 3 over 2 root 5, 3 over 2 root 5, 1 over 2 root 5, and 1 over 2 root 5. Okay, we'll just scale that down a little bit. Wish you could do that on the exam. And then negative 1 over root 6, 0, 1 over root 6, 2 over root 6. Still need to scale it down a little bit. Okay, this is our orthonormal basis. We will come back to this in a moment. We're not done. Great. Hey, that was pretty good. I didn't know how much space that problem would take up, so I left like 2 pages and we almost filled it. That's pretty good. Right. So now, next example is nice. Find an orthogonal basis for R3, which contains a very particular vector. So you want an orthogonal basis for R3, but I also have a vector that I want in that basis. Well, Gram-Schmidt requires us to start with a basis and then go from there. So any basis should do. V1, we'll make V1 x1. But x1, x1 is 1, 2, 3, like we were saying. We can take x2 and x3 to be anything. So I'm going to take them to be e2 and x3 to be e3. x3 to be e3. That is 0, 1, 0, and 0, 0, 1. And hope for the best. Okay, great. So this is v1. v2 is 1 is 1, 2, 3 minus okay. I'll put it, so we need to do the projection of e2 onto 1, 2, 3. This is not going to be great. Okay. I'll just write it this way. E2 could do x2, whatever. Dot v1 over v1 dot v1. Oh, all times v1, which is, and also v2 is e2 minus this. I apologize. I got the rule. I was committed to starting with x1 is like e1 or something like that. No, we have to start with v1. Like if we want v1 to be contained inside of this orthogonal basis, we can't go projecting it onto other factors, right? We have to start with that one as our x1, and then go from there. Okay, so this is 0, 1, 0 minus e2 dot v1. That's just 2, right? Just dot these two, just dot v1 and e2. v1 dot v1 is 1 plus 4 plus 9, which is 14. Uh-oh. Times v1. Okay. So this is going to be negative 1/7, and then 1 minus 2/7, so negative 5/7, and then 0 minus 6/4. Oh, 0 minus 3/7, negative 3/7. I'm going to go and scale that thing up, and I'm going to scale it up by a factor of negative 7. After all, it's only asking us for an orthogonal basis, so any multiple of this vector will do. So I'm getting 1, 5, 3 as our v2. v3. v3 is going to be e3 minus e3 dot v1 over v1 dot v1 times v1 minus e3 dot v2 over v2 dot v2 all times v2. Okay, let's just put in all the information. So e3 is 0, 0, 1. e3 dot v1 is 3. v1 dot v1 is still 14. Times v1, which is 1. Yeah, 1, 2, 3. Jeez, thought we made a computational error. By the way, if ever there was a time to doubt your computations and like double check to make sure you didn't do any computational errors in the process, this is one, because you make one error and it will factor all the way through your problem. So be careful. Great. And minus e3 dot v2 is just the third component of v2, which is 3, divided by v2 dot v2, which is 1 plus 25 plus 9, 35. times v2. 1, 5, 3. I literally said the thing about checking your computation. I'm almost positive there's an error here. 2/14 is 1/7. Negative 2/14 is negative 1/7. Times 2 is negative 2/7. Plus 1 is positive 5/7. And if you didn't catch my error, we would have been in a lot of trouble. And we've gotten the problem wrong. Okay, which means that when I scaled up by negative 1/7, I missed a negative sign there. However, that does not change the dot product. It doesn't change E3.V2 or V2.V2. So actually, we're fine. Let's keep going. Okay, great. So this is now oh, by the way, when you're rescaling, like we did here, make sure that that's the last thing that you do. You have to do the vector subtraction, whatever, first. You can't like do the projection onto do the perpendicular component or whatever, and then scale in the middle of that computation. You can only scale at the end. So this vector that we're going to write down is going to be gnarly. So negative, I'm looking at negative 3/14 minus 3/35, and then negative 6/14, so negative 3/7, plus, here's the plus, 3/7, positive 15/35. Wow. Okay. And then 1 minus 9/14 minus 9/35. Okay, that's not as nice. We can do some arithmetic though. So notice the common denominator of 7 everywhere. That's what we got to work with. So negative 15/70 minus another 6/70. That's 21/70. So negative 3/10. We're going to check our final answer. Actually, I think we can just look. Yeah. Okay, we can cheat. 0, by the way. Nice. And then, okay, 9/14 is 45/70. 9/35 is 18/70. 45 plus 18, 63. So it'll be 70 minus 63. Wow, 1/10. Which we can then scale up to negative 3/01. Looking good. Okay. And so orthogonal basis. This is a basis for R3, right? So it'll be 1, 2, 3, of course. 1, negative 5, 3, negative 3, 0, 1. Pretty good. It's a pretty good resounding conclusion. So the very last thing that we have is something called the QR factorization. QR factorization is incredibly useful, especially if you want to like use a computer, for example, to compute eigenvalues or something like that. Essentially, so they give the QR factorization as a theorem. Oh, okay. There's one thing that's missing in this theorem. I'll just tell you what the theorem is. So the theorem says let A be an m by n matrix with linearly independent columns. The thing that's missing is that the number of rows has to be greater than or equal to the number of columns in order for this to work. How are you going to have linearly independent columns if the number of columns is greater than the number of rows? Right. So that's why it's okay. I guess the linearly independent columns thing forces m to be greater than n. Anyway, then A can be factored as Q times R, where Q is an m by n matrix with orthonormal columns, and R is an n by n invertible upper triangular matrix. So upper triangular matrix without any zeros on the diagonal. Then it just says, okay, so we no proof. We just have an example. Do it for this one. Hopefully you notice the columns of A are the basis vectors for the subspace that we did for the first example. So I'll just tell you what Q is. Q is the matrix that you get when you just find an orthonormal basis given the column for the column space of A. Okay. Let me just. I'm gonna have to copy these. Actually, I think I can copy them out of the book because we got our answer right at the end of the day. Okay, so right, 1/2, -1/2, -1/2, 1/2. I'm going to use their rationalized fractions. So 3 root 5 over 10, 3 root 5 over 10, root 5 over 10, and root 5 over 10. And then the third column was negative root 6 over 6, 0, root 6 over 6, root 6 over 3. Again, if you're wigged out about where I just pulled those out of nowhere from, scroll up to the previous example, take those columns, and you can put those columns in place of Q, in place of the columns I'm using here. But I didn't want to just make you dizzy by scrolling up and down, so I just copied out of the book. But the book rationalized their fractions, so they made sure that the denominator was a rational number. Okay, that's fine, I guess. Okay. And now what? Okay, so now we have to find an upper triangular matrix R that's invertible that satisfies this property. So notice that A equals QR, where Q satisfies the properties of this matrix Q. Well, if that's true, we also know that from a theorem from 5.1 that Q transpose Q is the identity. You take Q transpose and you multiply it by Q, you will get the identity. Right? That's by a property. That's because orthonormal matrices, if you dot them with, so you take Q and you take Q transpose, multiply them together, you're multiplying essentially all columns of Q with every other column of Q, but turned sideways into a row. And whenever you multiply a column in an orthonormal basis by itself, you get 1. And when you multiply a column in an orthonormal basis by another column, whatever, you'll get 0. So you're going to get a square matrix of zeros everywhere except for on the main diagonal, you'll get 1s. That's the identity. You can verify this if you are still dubious. Okay. So now what do we have to do? We want to find R. Well, notice that A is equal to QR. So Q transpose times A. So I just multiply both sides of this equation by Q transpose. Multiply on the left by Q transpose. So Q transpose A times Q transpose Q R is, well, Q transpose Q is just I, but IR is just R. So in other words, R is just Q transpose times A. Okay, let's just do it. Not afraid. 1/2, negative 1/2, negative 1/2, 1/2, 3 root 5 over 10, 3 root 5 over 10, root 5 over 10, root 5 over 10, negative root 6 over 6, 0, root 6 over 6, root 6 over 3, times our original matrix, 1, negative 1, negative 1, 1, 2, 1, 0, 2, and 2, 2, 1, 2. Notice what we get when we're done will be a 3 by 3 matrix, because this is a 3 by 4 times a 4 by 3. Also, I didn't check it at any point in this argument, but just verify to yourself that all the dimensions of all the products of all the matrices line up and that all the products are actually defined. They are, but check anyway. Okay, let's go. And so this should be upper triangular. Let's do it. Okay, so 1/2 plus 1/2 plus 1/2 plus 1/2 is 2. Notice I have a pair of opposite signs and a pair of opposite signs, and matching. So next entry will be 0. The third entry will be negative root 6 over 6 minus another root 6 over 6 plus root 6 over 3, also 0. The next one we expect to be the next diagonal entry will be non-zero, but this next, I guess, 1, 2 entry. So 2 times 1/2 is 1, minus 1/2 is 1/2, 0, and then plus 1 is 3/2. That's not so bad. The next one we expect to be a non-zero number. 2, oh god, okay. 2 times 3 root 5 over 10, that's 3 root 5 over 5, plus 3 root 5 over 10. Okay, wait, that's 6 root 5 over 10 plus 3 root 5 over 10. Together that's 9 root 5 over 10. And then plus 0 plus another 2 root 5 over 10 is going to be 11 root 5 over 10. Did we do that right? 210. No, okay. This is close. Fortunately, I miscalculated. So that 0 should have been a 1. I miscopied this guy here, but not above, because we computed these columns correctly above. And then just now, when I computed this 0, I miscalculated, but correctly, so that we would end up with a 0. Okay. However, this 3/2 is probably wrong. Instead of 3/2, it should have been 1 minus 1/2 plus 1/2, so just 1. Great, that's way better. Also, 9 root 5 over 10 plus 1 root 5 over 10 is 10 root 5 over 10, which is just root 5. That's way better. And then our third entry will be 0, but let's just check it anyway. It'll be negative 2 root 6 over 6 plus root 6 over 6 plus root 6 over 3. Sorry. Negative root 6 over 6 plus 0 plus 0 plus root 6 over 6. So in other words, this guy and this guy cancel. Those two guys will give you the same number, which will cancel. And then this bit and this bit, both the products are literally 0. So 0. Okay, good. And then our last one, 1 minus 1 minus a half plus 1 is 1/2. Positive a half. The next one could be anything. 6 root 5 over 10 plus 3 root 5 over 10. Oh, sorry, plus another 6 root 5 over 10 is 12 root 5 over 10. Plus another 1 root 5 over 10 is 13 root 5 over 10. Plus another 2 is 15 root 5 over 10. So 3 root 5 over 2. Could have been worse, I guess. And then our last one will be negative root 6 over 3, 0, root 6 over 6, and then 2 root 6 over 3. So it's positive root 6 over 3 plus another 1 root 6 over 3, which is root 6 over 2. Okay, there's R, and here's Q. And that's it. That's all that we need to do for a QR factorization. Once you've computed an orthonormal basis for the column space, just stick those basis vectors in a matrix, take the transpose, multiply with your original matrix, and you will magically produce an upper triangular matrix that satisfies this QR factorization. And speaking of which, that's it for this video, and that's it for chapter 5. So next time we'll just start out with chapter 6. We'll start talking about some more abstract topics, and chapter 6 is as far as we'll go in this class. But I will see you in the next video.